Introducing Thetis, the world's first DLS that simultaneously measures particle size and shape. Let's take a look at how conventional DLS works. Small particles move continuously in a random fashion. That's called Brownian motion. The intensity of laser light scattered by small particles is measured as a function of time. Those data are converted to an autocorrelation function, which determines the translational diffusion coefficient d. The Stokes-Einstein equation converts that diffusion coefficient to an equivalent spherical diameter. But what if my particles look like this? Scattered light from non-spherical particles can be separated into two components, a translational component, dt, and a rotational component, dr. But what if we utilized a polarizing lens to separate the scattered light into two components, VV and VH, then analyze them independently? If the particles are round, we observe no light scattered on the VH detector. However, if the particles are not round, then we will observe variations in the intensity of light on the VH detector. Two diffusion coefficients, dt and dr, can be determined from the scattered light from the dual detectors. From these diffusion coefficients, we can determine the length and width of the particle. Let's compare two different nanorods measured using dynamic DLS with Thetis and transmission electron microscopy results, the gold standard for nanoparticle shape. The agreement for both length and width of these two samples is outstanding, especially given the fact that these two techniques are so radically different in approach. Thetis is simply the best DLS money can buy. Nanoparticle size and shape in one device, static light scattering and dynamic light scattering, software correlation with high-speed data acquisition, multimodal, discrete, and continuous algorithms, simply the most versatile DLS in the world. Call to arrange a demonstration today.